So, yesterday I showed you some HR diagrams of the evolution of most stars, 1 to 8 to 10 or so solar masses. And planetary nebulae is the final stage of stellar evolution for most of these stars. By the time the star reaches the planetary nebula stage, nucleosynthesis ceases, and the star transitions to becoming a hot, ultraviolet-emitting white dwarf star. Remember, this has evolved from these situations where we have a star and a huge circumstellar envelope of molecules, and this material that's been thrown from the star as a molecule and dust continues to flow away from the star, but now the star becomes a white dwarf. It's shed most of its atmosphere, it's emitting a lot of ultraviolet radiation, and this remnant gas from the previous circumstellar envelope phase, the AGB phase, becomes highly ionized. And so you go from a situation where you have an AGB star with its envelope full of molecules of dust to a situation that looks like this, a planetary nebula, where you have a small white dwarf in the center, and the material's flown away, and the ultraviolet from the white dwarf has really ionized a lot of the material. The temperature of the star becomes very hot in the AGB phase. The photospheric temperature may be 2,000 Kelvin. By the time it becomes a white dwarf, it's more like 100,000 Kelvin. And planetary nebulae evolve on the order of 10 to 12,000 years. That's their lifetime. So if you remember the HR diagram that I put up yesterday showing stellar evolution of most stars, that's at the very end. So main sequence, red giant branch, asymptotic giant branch. We go through a transition stage between the AGB and the planetary nebula stage called the protoplanetary nebula. I'll mention that in a moment. And that's another interesting phase, which I won't talk too much about, but I want you to be aware of it. In the protoplanetary nebula phase, all of a sudden the mass loss becomes much more violent. It increases. The star starts stripping its material off. It's emitting a lot of ions. The gas around the star becomes ionized, and then it evolves into the planetary nebula phase. So the protoplanetary nebula phase also involves some interesting chemistry involving shocks and high velocity winds. But it's even more short-lived than the planetary nebula phase, only a few thousand years. And so there's very few known protoplanetary nebula, maybe 20 or so, but a lot more planetary nebula. And that's just an example of protoplanetary nebula, the frosty Leo. Okay, so why are we interested in planetary nebula anyway? Stars have died, so what happens? Well, actually, it's mass loss from evolved stars that supplies about 85% of the material into the interstellar medium. People typically think that supernovas supply most of the material, and they only supply about 10%. And so if you add it up, there's a lot of material that comes out through the asymptotic giant branch into the planetary nebula phase, and then this material ends up in the diffuse interstellar medium, which forms the material that forms diffuse clouds, which collapse eventually into dense clouds. And so evaluating what comes out of the ejecta of planetary nebula is really crucial to understanding the chemical evolution of the entire interstellar medium. But when one thinks of planetary nebula, they think of these bright objects that are brightly colored because they contain emission from highly excited atomic lines and a lot of highly ionized lines. O2 plus is one of the very famous lines used to study in N plus and so forth. And this is what you see when you see pictures of them. Of course, they have nothing to do with planets, and so the name planetary nebula is an oxymoron. So one wonders then, you go through the circumstellar envelope phase, the AGB phase, all this material is lost from the star, it goes into planetary nebulae. What becomes of all the molecular material and the dust that was there? Does it all get reduced to the atomic phase and then thrown into the interstellar medium? Or is there some part of this material where molecules are preserved? And that's the question. Now, way back when, there was a paper by Tom Parquist and collaborators that actually predicted that molecules would be present in planetary nebulae, but since then there have been a few other molecules that said quite the opposite. Now, the UV radiation coming from the central star of the nebulae, as they become a white dwarf, is very intense. And it's predicted that large-scale photodissociation occurs of the material surrounding the white dwarf, and that the overall molecular content, which is a remnant from the previous asymptotic giant branch phase, basically decreases with time. You may see an early increase in some radicals and ions, such as shown here, due to photochemistry because of the ultraviolet radiation from the white dwarf. But after on the order of 10,000 years, the lifetime of a typical planetary nebula, the molecular abundances are extremely low. And this is what models predict, one by Redmond et al., another by Ali. Here we see CN peaking at about 3,000 years into the planetary nebula phase and rapidly dropping. And you see here charts of molecular abundances, numbers of molecular abundances relative to H2 of various molecules at various phases at 2,500 years, 6,300 years, and 10,000 years. And you can see if you picked up a typical molecule observed in AGB envelopes such as CN, you see it dropping from a few times 10 to the 6 relative to H2 to a few times 10 to the minus 10. And even more so for something like HCN, 10 to the minus 5 at the beginning of the PNE phase, down to 10 to the minus 12, a drop of 7 orders of magnitude. So this is basically what models predicted. So by the time you get to the end of the planetary nebula phase, that previous molecular content, in theory, should be reduced to atoms for the most part. But when one looked at the early observations, one got the impression that this might not quite be the case. Because if you look at some planetary nebula were studied, such as this one, the famous Helix nebula, which is actually a bipolar nebula, not a helix, it was studied in H2 not too long ago, and there was all these clumps of molecular hydrogen. This is molecular hydrogen viewed through its vibrational transition at 2 microns. And so you can see there are clumps of H2 present, so there's still some diatomic molecules. And then a map was made of carbon monoxide across the helix, shown by these contours here, and you can see there was a lot of carbon monoxide. So maybe there were some diatomics left in the planetary nebula. The helix is quite old, it's 10,000, 12,000 years old, so it's a very old nebula for comparison, and you can see that CO and H2 have been observed there. And this is true of some other nebula as well. Here's K345, just some common variety, quadrupolar planetary nebula. You see maps of, you can see it in H2 and CO, as well as N+. So maybe there are diatomics there. But the question is, well, okay. And furthermore, there were surveys done early in the, around 2002, 2005, and so forth, by Pat Huggins, who basically looked for CO in almost every planetary nebula that was in the galaxy, well over 100. And he detected CO in quite a few of them. And you can see some of these spectral lines have quite some different interesting velocity profiles. That's because a lot of the planetary nebula are bipolar or multipolar. And then you also see that some of the lines look rather ratty, and that's simply because of galactic contamination, because a lot of the planetary nebula lie on the galactic plane, and so you get absorption and interfering lines from clouds that lie along the line of sight. So CO was present in, I don't know, about 75% of the nebulae that Pat Huggins observed. And then there was also a study not too long ago of NGC 7027, a very young planetary nebula. It looks like this. It has a quadrupolar structure. And this was the only one studied in any detail outside of CO and H2. It's rather young, 700 years old, right onto the PNE phase. The star's pretty hot, about 200,000 Kelvin. And when there were surveys done of this planetary nebula of molecular lines in 2002 by Herpin et al., and this is what he saw, and this was with in the infrared, and he saw things like CH and OH. So there are other molecules present, CH+. And then more recently, Zhang and Kwok studied it via millimeter wave lines, and so they looked for common things like CO, of course, which was seen, CN, they found HC3N, and a few other molecules. This is a spectrum taken in the 1 millimeter region. You can see really it's rather sparse in comparison to a similar spectrum taken in IRC plus 10216 over the same wavelength region, which is full of lines. But the molecular content was far more than was typically noted. Zhang and Kwok found things like N2H+, Hc3N, cyclic C3H2, and so forth. And so this was hinting that there was more in planetary nebula than we had previously thought. There was some evidence of photodestruction in Zhang and Kwok's data. They found that HCN was weaker than either CN, CH, or CN, and so CN presumably forms from the ultraviolet photodestruction of HCN. But this was a young nebula. What happens in older nebulae? That was the question. So, not too long ago, I had a couple of interested students, and we decided to have a really close look at the molecular content of planetary nebula. So my student went into the Huggins et al. Papers and picked maybe 15 or 20 of the top ones. Another student studied some other ones. And they basically came up with this ensemble of nebula to study, ranging from very young to very old, such as the Helix, the ring. This is a very young one, K447. And you can see they have various morphologies. Many of them are bipolar, some of them are elliptical. So we sort of sampled a wide range of different types of planetary nebulae. And the idea was to pick common molecules, such as HCO+, CH, HCN, and so forth, where we could observe at least 2 transitions, and study them in all these nebula and see what we found. And after that, we did some more targeted studies of a few select nebula, which I'll also mention. And this was the work of Jessica Dodd. Lindsay Zach did a lot of work on the Helix, and the main planetary nebula person is Deb Schmidt, all graduates. And we did this survey using the telescopes at Arizona, the sub-millimeter telescope on Mount Graham, very good for 1-millimeter observations, and then a lot of it was done with the old 12-meter and now the new 12-meter in KP. So what did we find? Well, it was kind of amazing. We started looking for HCN, and in most of the nebula, we found it. This is some of the spectra we observed. We had about a 75 to 90% detection rate in HCN, also in HCO+. This is some more spectra of HCO+. And then we looked at CCH. In CCH, this is the 3 to 2 transition at 262 gigahertz. It has spin rotation doubling. That's why all these lines are doubled. So here are all the nebula CCH came moving through. And then HNC, that's just some of the spectra. Some more HNC. And in the process, we added a few more nebula, NGC 6772, which is an elliptical one, and then this multipolar one, NGC 2440. And almost every place we looked, we found HCN, HNC, CCH, HCO+, and even CS. And we determined an HCN to HNC ratio of about 1 to 8. So this is very similar to what's seen in diffuse clouds, by the way. And once again, you'll see evidence of galactic contamination in the 1 to 0 transitions of many of these molecules. But in the 3 to 2, as long as we were not looking at CO, things would be clean. So that was rather interesting. We didn't expect to detect these polyatomic molecules in these nebula, so we got ambitious and started studying some of them in more detail. And one of them was the red spider, shown here. It's about 1,600 years old. And amazingly, we found, of course, CS, HCN, HNC, but we started finding carbon-13 substituted species. We also found N2H+, well, that was seen in NGC 7027, but we found formaldehyde and SO. So that sort of added to the list of molecules that is seen in planetary nebula. And amazingly, we saw H13CN and HN13C, and we could determine a carbon-12 to carbon-13 ratio from those, and that was about 3 to 5, which seemed unusually low for a planetary nebula that has just come through the asymptotic giant branch and has mixed a lot of carbon-12 to the surface. And that's still a puzzle. Another interesting nebula we studied was M2-48. It's about middle age, about 5,000 years old. You can see its bipolar structure. Not a lot of observations of this nebula. And here we detected some interesting molecules as well, including SiO and SO2, as well as SO. And we didn't see CCH, which we saw in most of the other ones. And we recognized here that we're looking at nebula that's oxygen-rich. And so the molecular content of this planetary nebula reflects the carbon-to-oxygen ratio of the progenitor star when it was in the HEB phase. This one was obviously oxygen-rich and stayed oxygen-rich, and we see the molecules we see in some of those oxygen-rich circumstellar envelopes that are prominent. Once again, we were able to measure the carbon-12 to carbon-13 ratio, which is about 3 to 5, also very low. But this could also have become oxygen-rich through a process called hot bottom burning, so that might explain that ratio as well. And then, of course, one of the most interesting objects was the helix, because the helix is so old. And it's a real test of what happens to the molecules as a function of age. It's also old and it's close by, so it's spatially large on the sky. This extends over 1,000 arc seconds, so there's many beams, millimeter telescope beams across this nebula. So you can't study it, the whole thing at once. You have to study select positions that we did. And years ago, there was one position that was studied where they detected HCN and HNC. And so we decided to observe this nebula in multiple positions, in multiple molecules, including cyclic C3H2, and see what we found. This was a lot of the work of my graduate student, Lindsay Zach. And so we selected positions across the nebula, indicated here. Our first project was HCO+, along with formaldehyde, and we detected it at every position. Now these lines have really funny shapes because there's a huge velocity structure. This is a bipolar nebula, so it's two parts, one flowing towards you and one flowing away from you at a slight angle relative to the line of sight. So sometimes you'll get two velocity components at a given position, redshifted and blue shifted. And it's a lot more complicated than that, so sometimes the lines are broad, sometimes they're narrow, depending on how many clumps you're sampling in the velocity distribution. In addition to HCO+ and formaldehyde, we looked at HCN and HNC, and HCN profiles are complicated because of the nitrogen quadruple hyperfine structure. These are the 1 to 0 lines. Once again, we detected both lines across the nebula. And then cyclic C3H2 and CCH. And once again, CCH has a hyperfine structure, which makes the profiles even more complicated, but one could deconvolve that. And we were seeing it every position. In fact, we were so excited by what we were finding, we ended up mapping the whole nebula in HCO+, and here is the contour map of the molecular emission of the 1 to 0 transition. And you can see it traces, it's coincident with most of the ionized material, except in the center, which is blue, which is traced by the most highly ionized atomic gas by helium+. So where the blue is, that's helium+, that's highly ionized. But the gold and the yellow and the brown is sort of emission trace a combination of N+ and O2+. And you can see that the molecular gas lies across the same region as the atomic gas. And what we believe is that, and we have this from observations, for example, in formaldehyde, we ended up observing 5 different lines, ortho and para, from the 1 to 0, 2 to 1, and 3 to 2 transitions, and we're able to do some radiative transfer on it. And the density of the molecular gas in the helix is about 10 to the 6 particles per cc. So we believe the molecules are embedded in dense clumps, which are mixed with the ionized gas. Okay? And those clumps are hot. If you look at the temperatures from the radiative transfer analysis, it's typically 20 to 40 Kelvin. So we've got cold, dense clumps embedded in a hot ionized medium, very similar to what they see often in photon-dominated regions. And the interesting thing is, for example, we measured the CCH to cyclic C3H2 ratio. It was 5 to 8, an average value of 29 plus or minus 7, which agrees exactly with what is found in diffuse clouds, 28 plus or minus 1.4. Now, there's a lot of dispersion here, but I'll bring diffuse clouds in later on in this talk. And just to show you where we observed all the spectral lines to make this map, here is the map of 1 to 0 HCO+ with all the individual spectra. You can see the lines are all over the place. There was one other extremely interesting nebula, which is new stuff that we've observed lately, mostly with the around 30 meter, which was K447. Once again, this is one of these nebulae that's never been studied. There's a few papers on it, that's it. And my student Jessica Evans got very interested in it, and Debbie Schmidt followed up. But this is another young nebula. It's about 900 years old. I can't show you a pretty picture. This is the only image one can find in literature on it. And this is Seaman N+. And it's very bipolar, and it's very small. The scale here is 5 arcseconds. In the center is the star, and it has these bipolar lobes, obviously traced in N+. And some sort of bipolar outflow coming from the central star. We initially observed it with our smaller telescopes. Oh, that's just the distribution. H2 has been seen here too, and H2 molecular hydrogen traces those bipolar lobes seen in N+. And we got some very interesting results when we observed it with a 30-meter. This is at 2 millimeters in wavelength. You can see there's lots and lots of spectral lines, which we didn't expect. In fact, and that's Debbie Schmidt's work. In fact, it was most interesting. Not only did we see many lines of HC3N, but we saw doubly carbon-13 substituted species with all the different combinations of carbon. So the first 2 carbons, the last 2 carbons, and the N carbons, all detected in HC13. And this is about the only source where you see all these different isotopologues observed together. We also found some very interesting new molecules for Planetary Nebula, methylacetylene, methylcyanide, and CH2NH, which was quite a surprise. And this is among the lines seen in the IRAM data. So here's just some more spectra, just to show you. There's our carbon-13 substituted HC3N lines, HC3N. You can see all the carbon substituted lines, CH3CN. And this is another source where we have about 10 unidentified lines that we don't know what they arise from. Probably some weird molecular ion that is yet to be measured in the lab. We even see things, by the way, as 13 substituted formaldehyde and so forth. So it's a really complex spectrum for a source that's not supposed to have any molecules. And then here are some of the individual lines. There's N2H+, CH2NH, there's one of the lines, another one of the lines. We also saw SiO in this source, and formaldehyde, CH3CN, and so forth. Very convincing spectrum. And so here's sort of a list of these molecules now we've seen in this Planetary Nebula. And you can see we've got a lot of carbon-containing molecules with complexity we've never expected, and many, many carbon-13 substituted species, which is just amazing for us to find. And obviously this source is extremely carbon-rich and almost looks like the molecule seen in TMC1, the torus molecular cloud, which is known to be very carbon-rich. So it's a huge reservoir of carbon-bearing species, and so we can only conclude that the progenitor, AGP star, was one of these carbon stars, and the carbon enrichment simply survived. Now, another interesting thing is that you see all these carbon-13 substituted lines. Well, there were some other interesting isotopic detections. We were able to measure HC15N. Remember, the 14 to 15 ratio that's predicted for CNO cyclonucleosynthesis is 30,000, okay? Measurements of HC15N relative to H14N gave us an N14 to N15 ratio of 13. Huge enrichment of nitrogen-15. And we're not worried about opacities here because we had enough lines to model it and, take the HC12N lines are a little optically thick, but we can correct for that in the radiant transfer modeling. And then we also found C17O. And here's the 2 to 1 line and the 1 to 0 line, HC15N, 1 to 0 line, 3 to 2 line. And so we were able to find an oxygen 16 to 17 ratio of about 21, and then the carbon 12 to carbon 13 ratio is about 2. So here's HC13N and H13CS. So we measured the carbon 12 to carbon 13 ratio of various molecules, and so we believe our errors on these are pretty good. So this was an amazing isotopic enrichment. In fact, this is probably the largest enrichment of nitrogen-15 and oxygen-17 seen currently in an astronomical source. The only source that comes anywhere near it is this very interesting object, CK Vol, which no one's quite sure what it is. Supposedly, K447 is a planetary nebula. And its low carbon-12 to carbon-13 ratio suggests that its progenitor star was one of these weird AGB stars called J-type stars. These J-type stars, like a lot of AGB stars, are carbon-rich, but they also have extremely high carbon-13 enrichment. And this is maybe what's happening in this case. But what causes the enhancement of carbon-13 and oxygen-17 at the same time, and nitrogen-15? Well, the only way you get nitrogen-15 enhancement is the hot CNO cycle. So you've got to have some kind of explosive process to produce nitrogen-15. And so we were beginning to wonder whether this nice picture of AGB stars evolving nicely into planetary nebula is not quite correct, that there's some more nucleosynthesis that occurs at the end of the AGB phase, where you have some explosive helium flash, which basically adds protons to 14 and 12 and produces nitrogen-15 and carbon-13 and oxygen-17, which are explosively ejected before they react to form something else. But that's just like speculation. We also now have some very nice ALMA images of planetary nebula. John talked about ALMA, I'm sure other people did. This is work in preparation. This is just one example. This is one of the nebula we studied via single dish. So you see HCO plus lines and HCN lines. And we actually imaged them in those 3 molecules with ALMA. And here's an optical picture of the source. The 28 arc seconds here shows the beam observed in HCO plus 3 to 2 and HCN 3 to 2 with our single dishes. And here are the ALMA images. And you can see this is a bipolar nebula. What the ALMA images seem to suggest, and they basically are maps of this inner region, that there's another bipolar outflow perpendicular to the one seen in the optical image, and clearly seen in HCN and HCO+, which look almost identical in their maps. And so we have a few other sources imaged, and we're working on that material right now. So now, after 10 years of observations, we have enough molecular abundance measured in 22 odd planetary nebula that we can plot molecular abundances as a function of planetary nebula age. And here is the plot. So what you see in the dashed lines is the theoretical predictions. This is that's the model for HCN. It just decreases HCO plus and which is the blue HNC, and this is HCO plus. And you can see as a function of age, ranging from the beginning of the planetary nebula stage to the end, a span of about 12,000 years. Models predict the abundances decrease, and here are all our measurements. We have CS in there too, CN, cyclic C3H2, formaldehyde. And for the most part, the abundance are fairly constant across age within an order of magnitude. We haven't been able to explain this. So molecular abundances apparently remain constant, or fairly constant with age, in contrast to theoretical predictions. And I've been trying to get a theorist to work on this, and they seem to be hesitant to do so. So we seem to have a new paradigm here. We have another whole big set of sources that are molecular rich in an extreme interstellar environment. From what we can tell so far, molecules are pretty widespread in planetary nebula, although we only have a sample of 20-some-odd sources. We're increasing that now. And we have a lot of polyatomic molecules, even CH3CN and CH3CCH, amazing given their molecular complexity. Furthermore, the abundances remain relatively constant with age, so they're not all photodissociated. So like I said, we believe that the molecules mix with the dust and form these really tight clumps that are pretty dense and self-shielding, and they just last a long time. And this means that at the end of the PNE phase, when this material enters the interstellar medium, it enters, at least in part, as molecules, not just atomic material. And this is quite an interesting thing, because remember, you start with a 1 to 8 solar mass star. A white dwarf is typically half a solar mass. The ionized material is not very massive. It's only a few tenths of a solar mass. And so you have something like half to 7 solar masses of grain and molecular material that's ejected in diffuse clouds. So here's the current list of molecules I've seen in PNE. We've done a lot of these observations, but these objects are also sources of interstellar fullerenes, C60. It's very interesting molecular content. So what this seems to suggest is that we have planetary nebula injecting their material into the diffuse interstellar medium and its molecular content. And this could explain a lot of observations of diffuse clouds. Harvey List and collaborators, along with people like John Mayer, have observed a lot of molecules in diffuse clouds. They're polyatomics. And they're so complex by interstellar standards that the abundances can't be explained by in situ formation in the diffuse clouds. It's thought that they have to be formed somewhere else. And so our explanation is they just arise from planetary nebula ejecta. They're just ejected into diffuse clouds, and they're ejected in clumps, and the clumps slowly disperse. But there's enough material left over such that they're seen in diffuse clouds. Now, we didn't know polyatomic molecules even existed in diffuse clouds because the densities are so low that the usual collisional excitation mechanism doesn't work. And so Harvey List was able to detect these by observing them in absorption against background quasars. And that's the only way they were found. And I remember him giving a talk about 50 years ago, and he's saying, well, I'm seeing HCO plus everywhere, and it was pretty amazing. Anyway, if you look at the relative abundance of what we measure in planetary nebulae versus what are seen in diffuse clouds, you see about an order, well, so this is the Helix nebula, the oldest one that we've studied, relative to diffuse clouds. You see the abundance has dropped by an order of magnitude or two, which is consistent with the stuff being ejected into diffuse clouds and slowly dispersing. We also note that C60 and C70, these Fullerene molecules, are found in several planetary nebula, and there's also a lot of speculation that C60 plus is seen in diffuse clouds, and how did that molecule get there? Well, once again, it could be from ejecta of these two molecules from planetary nebulae. And so one should really perhaps look to what's seen in planetary nebulae to deduce what might be the carriers of the diffuse interstellar bands, which I'm sure we'll mention sometime in these lectures. But there's more to come because we started looking at another 10 nebulae, and here are just pictures of them. And once again, we've been finding things like HCO plus and HCM. Here's some spectra taken towards NGC 6445 and M1-59. You can see that they're very complex nebula with multipolar flows. And so the more we look, the more molecules we find in different nebulae. So there may be a whole lot more nebula that are full of molecules, and we can measure abundances pretty easily. So I mentioned fullerenes, and I want to finish up this talk just with a little digression because fullerenes were originally detected in planetary nebula, and this is a spectrum taken by Jan Kami towards the planetary nebula TC1. This was one of the first real detections of fullerenes. The black lines are the interstellar spectra observed in the infrared near 10, 15, 20 microns. And here's the predicted spectrum of C60. You can see it lines up pretty darn well, and then C70. And this was, as I said, done in the infrared. And so C60 and C70 have been seen in planetary nebula, and also some evolved stars as well. And that's what it looks like. And it's quite interesting that one sees them in space, because if you look at the fullerene chemical literature, they always consider fullerenes as artificial compounds, yet they're naturally made in interstellar space. And so one wonders what other molecules like that might be present. We seem to have a huge dichotomy from simple molecules observed in planetary nebula, and then a big jump to C60. Now, one of the big questions is, what lies in between in terms of chemical complexity? So, this got me thinking about how in the world do you form C60, bring 60 carbon atoms together in an environment where there's 10,000 times more hydrogen. Why doesn't hydrogen get involved? And this has been a question of other people. How are interstellar fullerenes formed? How does a pure sp2 hybridized carbon structure form a hydrogen-rich gas, which also contains significant amounts of oxygen and nitrogen? There's some thought that they come from PAHs, which someone probably brought up, these very planar polyaromatic hydrocarbons. But one has to take these planar structures to form a buckyball and strip the hydrogens down and then fold them into a ball, which is a very highly energetic process. That's a speculation. Another origin might be what they call HACs, hydrogenated amorphous carbon. Once again, though, you have to dehydrogenate them, and then once again, there's strain from folding structures into balls, and there's some question of whether HACs are there. And so I had a student, or have a student named Jacob Brown, who got very interested in this problem. And we were talking to one of our collaborators over in material science, who actually works a lot with graphene and fullerenes, and he suggested Jacob go look at the material science literature. And we found from reading the material science literature that people like to make discs of silicon carbide, and then they heat them, and it releases silicon atoms and leaves a graphitic structure behind. They use this for semiconductor fabrication. There was also evidence that you got both nanobud and nanotube formation with sufficient heating. If you look back at some of the literature, you actually see this. But you need a particular crystal structure of silicon carbide. Silicon carbide has like 50 different crystal structures. You need something called 3C cubic. And this is what the 3C cubic structure looks like. Oh, now my computer's. This is what the 3C cubic structure looks like. These are other structures of silicon carbide. The silicon atoms are the larger atoms, and then here's the carbon. And if you can see, if you strip out the silicon atoms, you end up with 6 carbons, and they form basically a 6-membered ring. And so you can produce graphite from removing the silicon, which you can do by heating. Graphite requires 6-membered carbon rings. However, if you want to form a nanostructure or a buckyball of fullerene, you need both 5 and 6-membered carbon rings. But this can happen also when there's irregularity on the silicon carbide surface. And some people in the material science literature have actually grown nanotubes. And here's a picture of the nanotubes. This is work done like in the 1990s. So here's a TEM image of nanotubes growing off the silicon carbide discs. Well, it turns out that silicon carbide, of course, silicon carbide grains are extracted from meteorites. And the most common form of silicon carbide grains are the 3C cubic. And so one begins to wonder whether silicon carbide grains formed in circumstellar envelopes could be the interstellar source of C60. And to test this, we collaborated with our friend Tom Zaga from the Lunar and Planetary Lab, who's an expert in transmission electron microscopy. And we decided, well, what we're going to do is take, synthetic 3C cubic SiC in little grains, which are the same size as grains extracted from meteorites, and we're going to put them in the transmission electron microscope and heat them and shock them and see if we can remove the silicon and find out what is left behind. And so we did this. We had analog grains about 46 to 65 nanometers in size. We put them under a vacuum, similar to what is seen near the photosphere of dying stars. And then under vacuum, we heated the grains to 1,000 degrees. We also bombarded them with 150 keV xenon ions. Now, at first I was opposed to this, but it turns out when you talk to planetary scientists, you learn all kinds of things. There's all these inert gases like argon and neon, which are found embedded in grains they extract from meteorites, which suggest these sorts of energies. So this is another instance where we're simulating conditions in circumstellar envelopes. And when we study these in the DEM, where of course you make images, you don't measure spectra, we solve this. So here's a given grain. There actually are 2 grains on top of one another. And after we heated it, this is the sort of granular structure of SiC, but as you heat it, you start getting striations along the edges, and this is the formation of graphite. And you can actually see the planes of the graphite and their distance apart, which is 0.34 nanometers, characteristic of graphite. We also did some solid-state spectroscopy that showed it was graphite. But in addition to this planar structures, we started seeing little nanobuds. And they have the exact diameter of C60. Now, it's not so easy to image individual C60 molecules with transmission electron microscopy. If you look in the literature, they're usually attached to something. So here's a C60 attached to a nanotube, and you can see the structure here is identical to the structures we're seeing along the edges of the silicon carbide grain. And so we have these hemispherical structures forming from silicon carbide, and once you get a hemisphere, it's pretty energetic to get a whole sphere, and you probably may be creating C60, which simply pops off the grain after a while. And there's also evidence of this process seen in actual pre-solar grains. One of our collaborators was studying a so-called graphite grain. When he sliced it in half, he found a distressed silicon carbide core. And so here's the grain. If you look in the center, which is blown up here, you can see this sort of distressed region. And this is an EDS map, and the green is the silicon, the carbon's in red, and that's the center of the grain here. So the grain has a silicon carbide core surrounded by carbon graphite. And that's just a pre-solar grain extracted from a meteorite. And so we think that the source of interstellar C60 is silicon carbide grains in the 3C cubic structure. These are readily made in circumstellar envelopes. We know this from the study of pre-solar grains. We believe that the silicon is stripped from the grains in the protoplanetary nebula phase. The mass loss is accelerated. You have shocks. You get this ion bombardment. And these sort of conditions raise the temperature, strip the silicon off the grains, leave graphite behind, and carbon nanostructures, nanobuds, and C60. It's the shock heating and the bombardment that disrupts the silicon carbide grains and removes the silicon. And this can occur in the presence of hydrogen. So this is what we believe may be the source of interstellar C60. In nebula like M2-9, the Butterfly Nebula is actually a protoplanetary. Okay, so that's the end of my talk. But I just want to show you that interstellar chemistry is extremely surprising. You can look at sources that are not supposed to have molecules, and they're full of molecules, and they're producing all kinds of interesting chemistry. So one should never just think that, I better be careful what I say here, don't necessarily believe the models always have a look. This whole planetary nebula thing is highly surprising to us. We did not expect to see molecules like this. It opens up a whole new avenue of chemistry. It also brings some explanation of what's happening in the diffuse interstellar medium. And so, we come up here and we speak like you know everything, but interstellar chemistry is always surprising. And if you get involved in the field, you'll find that as well. And so, just to thank group members and sources of funding and Tom Sega for his help with the C60 project and the Kuiper imaging facility. Thank you.